Science is a way of thinking, much more than it is a body of knowledge. One of the wonders of the science is that it is completely universal, which crosses national boundaries with total ease. With this note, I wish a pleasant morning to everyone gathered here and connected through online mode. It gives me prodigious pleasure in extending a warm welcome for the International Conference on Chemistry, Frontiers and Challenges, held in association with School of Engineering, University of Newcastle, Australia. Any change can be most accomplished through the power of prayer. Let's begin the program by invoking the blessings of Almighty.
यदक्षरं मात्राहीनं च यद्भवेत् तत्सर्वं क्षम्यतां देवि प्रसीद परमेश्वरी परमेश्वरी परमेश्वरी
I am pleased to invite Madam Dr. Yesodha Devi, Secretary, PSGR Krishnammal College for Women, to deliver the welcome address.
Very good morning and wish you all a very happy and prosperous New Year 2022. Thank you all for connecting with us for this international conference on chemistry, frontiers and challenges ICCFC 2022, organized in association with the School of Engineering, University of Newcastle, Australia. On this occasion, I feel proud to say and inform the audience across globe that our college has been ranked the 6th in the NARF ranking by Ministry of Education and accredited by NAC in the 4th cycle with a grade of A++ and with a score of 3.71. My sincere appreciation and congratulations to all those who involved in the process. The years 2020 and 21 have been difficult as well as different in terms of the pandemic situation and stay-at-home restrictions. In this scenario, this virtual conference would provide an international platform for renowned scientists, industrialists, and researchers to share their ideas in the broad areas of chemistry and applied sciences. I am happy to welcome Professor Dr. K. Natarajan, former professor and head of Department of Chemistry, Bharathiar University, and Dr. Bobby Kannan Mathan, University of Newcastle, Australia, and other resource persons from many national and international universities. Warm welcome to our principal, dean of different capacities, faculty members from various institutions, and students. At this juncture, it is my pleasure to welcome our speakers of the day, Professor Dr. K. Natarajan, former professor and head of CSIR, Emeritus Scientist, Department of Chemistry, Bharathiar University, Coimbatore, and Dr. Bobby Kannan Mathan amidst us today. Professor Dr. Natarajan has received his doctoral degree from the prestigious Indian Institute of Technology, Kanpur. Sir has served in various capacities at Bharathiar University, right from the head of department, dean, and dean of faculty of science, and then also there was the registrar in charge and controller of examinations, and as Emeritus Professor. He has published 178 research papers in referred journals and international and national journals. I feel proud to say that H index is 47, I-10 index is 132, and 7,151 citations, and RG score 41. Remarkable achievement. Congratulations, sir. Professor is a proud recipient of many international fellowships and is also a visiting professor to many international universities. And more above all these things, he is a good friend, philosopher, and guide, a well-wisher of our institution. And it's really an honor for us that he has accepted our invitation and he has come all the way here to be with us on this special day. I extend a warm welcome to you, sir. Thank you for taking part in this event. I am also very happy to welcome and introduce our speaker from Australia, Dr. Bobby Kannan Mathan. Dr. Mathan is currently a research academic in the School of Engineering, the University of Newcastle, Australia. Previously, he was an associate professor and group head of the Biomaterials and Engineering Materials Lab at James Cook University, Australia. He received his PhD. Welcome to you, sir.
Hello.
He received his PhD in Materials Engineering from the Indian Institute of Technology, Bombay, India, and worked at Helmholtz Research Center, Germany, and then at Monash University, Melbourne, for 2 years. He has published over 120 articles, including 1 book, 9 book chapters, and over 100 research articles. His papers are cited over 3,900 times, and his H index is 34. Recently, he was listed in the top 2% scientists in the world, published by the Stanford University along with Elsevier's Devi. So, hats off to you, sir. Congratulations. Dr. Mathan is a key reader for metallurgical and materials transactions and a reviewer for over 45 international journals. He has received many prestigious awards and fellowships. Our warm welcome and thanks to him for his participation, and also thank him for getting the collaboration from the university. I hope extend a warm welcome to you, sir, once again. Thank you very much for joining.
Thank you.
I hope these 3 days will be filled with abundant scientific discussions, which will lead to a number of new ideas and interventions that will benefit our society. My best wishes to the organizers and the participants for their successful and fruitful conference. Thank you.
Thank you, Madam, for the warm welcome. I request our Secretary, Madam, to honor the keynote speaker, Professor K. Natarajan. Thank you, ma'am, for your kind gesture. Now, I cordially invite our Secretary, Madam, to release the conference souvenir. The dignitaries on the stage will receive the copies. Thank you, Madam. Thank you, sir. I deem it a great privilege to invite Professor K. Natarajan, former head and CSIR Emeritus Scientist, Department of Chemistry, Bharathiar University, to deliver the keynote address. Sir, Kindly take over the podium.
Thank you all. It really gives me a great pleasure and it's my privilege to participate and to give the keynote address for the conference organized by PSGR Krishnammal College in collaboration with the University of Newcastle, Australia. First of all, I take this opportunity to congratulate the Department of Chemistry of this college for having taken an effort to conduct this international seminar on chemistry, frontiers and challenges. In fact, while congratulating the department, I appreciate the GRG Educational Trust and the management of the college for having supported it. You all know that without the support of the institution, nothing innovative, new things can be done. In that sense, PSG always the pioneer. I was a student of PSG College of Arts and Science from 1966 to 70. So I know how this family developed this institution. So it is also very important to look at the interest of the faculty of the Department of Chemistry. They have taken a lot of interest in doing so. So it is very unfortunate that most of the participants are not able to be present in the campus. A very beautiful campus, I will tell you. The participants, they miss. I must tell you that you would have really enjoyed being in such a beautiful campus. But because of the restrictions of COVID, that couldn't be done offline. On the other hand, it is done online. But at least, partly I am happy to be here this morning to physically be present for giving the keynote address. At least some of you, because you are always already there in this camp. Having said that, it is my duty to say a few words on this conference. Well, you all know that such a conference will bring many international experts in chemistry to give you the latest findings from their own research. Now, my dear young researchers, there is a possibility of going through all these findings from the journals that are being published frequently and regularly. But you know, one will not have enough time to go through all these things in addition to the work that a particular researcher is doing in his field. So this is an opportunity where you sit for 3 days and listen to different people and giving lot of results. The basic idea is that you will try to know what are very important. See, among the few lectures, maybe you will have about 15 to 20 lectures, out of which it depends on the individual to take an interest in a particular area. Now, that is also very important because unless otherwise you concentrate and you become an expert in a particular area, you will not be known. You will not be known for the society. So, it is an opportunity where you can choose your field of research. While giving a keynote address in such events, I always have the habit of reminding two things to the youngsters. And this goes to the young faculty members as well in different institutions. Number one, you must become an expert in your chosen area. The chosen area is yours. You choose your area, and what I mean to say is that you must become an expert. You should know A to Z in that field. Then only you can be able to perform very well. I will come to that little later. It is also very important, the point number two, to improve your communication in English. You know, however much you know, however great talents that you have, unless otherwise you communicate to other people, it is of no use. You may know so many things. You may be able to do a lot of things. But how will you know? How will you let others know that you can? You have these potentials for which communication is important. My dear youngsters, at least from India, though our medium of instruction is English, hardly people speak in English. The communication, to a very great extent, is not very satisfactory. So hence, I request the young researchers who are participating in this conference to develop a good communication in English. That is absolutely important. To give you an example, you know, there was a lot of pressure for Microsoft, Bill Gates. I don't know, many of you, whether you know or not, 45% of the people, scientists, work in Microsoft is from India. It is no wonder that Indians do have the knowledge, do have the brain to develop new things. I will give examples a little later that might inspire you. In addition to the knowledge that they have in their particular area of research, they have very good skill in communicating in English. That is why I sincerely say that you must improve your communication. And when the former president of US insisted and asked Bill Gates to employ people from America for his Microsoft, he said, I cannot do that. The real working force is from India. If you say that if you give me an order that I must only employ Americans for my company, I'm sorry, Mr. President, I will have to shift my company to Bombay. This is what he exactly said. My dear youngsters, please remember, this is not only due to the knowledge that our Indians have in a particular area, it is also equally important that they have the ability to communicate in English. Whether you like it or not, English is the international language. You will be surprised to know the countries where the education was in their mother tongue, say, namely in Japan, Germany, France, etc. They have now very recently switched over to English because the knowledge that they gain and they develop cannot be distributed to other people unless otherwise it is done through the English. That is why, my dear youngsters, in addition to requesting you to be an expert in a particular field, please try to improve your communication English. In that sense, when you get into the institution of your work, whether it is for learning or for research, see to it that you talk to your colleagues and your seniors only in English. That doesn't mean that I do not have love for my mother tongue, Tamil. Believe me, I studied 12 years of school only in English medium. When I entered for my pre-university course in 1966 in PSG College of Arts and Science, I was dumbbound. All the lectures were in English. I was not able to understand quite nicely as the students from the English medium. There were many schools from, money schools and Staines High School where the students came through the English medium. But still, one could have. So, my dear youngsters, even if you don't remember any proceedings from this conference, please remember that you should become an expert in a particular area and you should be able to communicate in English. That's very important. Now, having said that, I must tell you how you should become an expert in an area. To become an expert in an area of science, science I mean physics, chemistry, mathematics, and biology. They are very, very important basic science. If you look at any present technological development, it is the basic science research which is the basis. Hence, you must have very good basic fundamental knowledges in this basic science, mathematics, physics, chemistry, and biology. To give you a solid example how these branches of science are very important, branches of basic science is very important. I don't know how many of you know the Nobel Prize which was given in 2009 in chemistry. It was for Venkatraman Ramakrishnan. The name itself suggests that he must be an Indian. So he got the Nobel Prize for chemistry in 2009. He got it in chemistry. Basically, he did his BSc, MSc, PhD in physics, a crystallographer from Punjab University. He went to US. He did his research completely on ribosome. Look at it. How? See, the Nobel Prize Committee is no a fool. They know the work deserves recognition in chemistry, which means a man with physics, basically physics, working on biological molecule, biology, getting Nobel Prize in chemistry, it shows very clearly the interrelation from among these basic sciences. Hence, my dear students, if you look at any modern gadget or equipments, they have been developed only on very simple concepts in science. Look at the discovery of electron. How many things have come out of it? The fundamental discovery has led to a large number of applications. You know, I was taught when I was introduced to chemistry in the college at the pre-university level, atom is the simplest matter which cannot be divided. Atom cannot be divided. That is how I have been taught for my beginning in chemistry. Now, you know, in addition to the neutron, proton, electron, so many interatomic particles, subatomic particles are being discovered. There are so many particles. So which means the understanding of the fundamental is very important. If we critically analyze the advancement of any area of science and technology, it is not difficult to see that there are three scientific concepts which form the basis. They are atom, the byte, B-Y-T-E, and the gene. The atom for chemistry and physics, byte for the information technology, and the gene for the biology. Each represents, you look at an atom, the byte, the concept of information technology, the gene, the tiniest particle in human body or any living thing. They are the simplest, the tiny particle, which are the fundamental units for any matter in science, in chemistry and physics as far as the atom is concerned. And the information technology, you look at anything in computer science or information technology, the byte is the tiniest thing which gives everything for the development. And also the gene. It is for the whole biology, whether it is biology of human being or animal or for the plants, the gene, the tiniest particle is very important. Hence, my dear youngsters, it might look strange when we deal with so many things in life which are so highly developed. This gentleman, no, this man on stage tells that if you want to become an expert, you must know fundamentally all things about the tiny atom, the byte, and the gene. It is very important. When you know clearly all the fundamentals behind the atom, behind the byte, and behind the gene, you can do anything in life when you choose a research. So atom of the matter, the byte of the digitized information, and the gene of biology are very, very important. So in the process of practicing science, one should understand the property being the least divisible. I told you the tiny particle. This least divisible unit gives a strong value with such a strong force. Without an atom, you cannot have any matter in the whole world. The matter, the atom, that is very important. So unless otherwise you know the whole nature, whole property of the atom, you may not be really able to develop a matter for your applications. The simple fact is matter, information, and biology are inherently organized. They are not absurd. They are very well organized. That is why when these things are very well organized, unless otherwise you know how these tiny particles are organized, you may not be able to develop a new thing. Look at, when you can understand the organizational behavior of the smallest particle, You can look at the big things in your life, all kinds of applications. That means understanding of that smallest part is crucial to the understanding of the whole. The same analogy is applied to the understanding of the relationship between science and technology. You know, science the basis, technology is the application. Basic scientific information is the tiny unit through which the technological development has been achieved. Basic science and technology have always progressed together. Since the dawn of modern science, fundamental discoveries, fundamental discoveries based on atom, byte, and the gene motivated the curiosity which led to the development of new tools, which in turn have increased our ability to investigate the nature, leading to further discoveries. What I mean to say here is, from the fundamental knowledge, we have developed fundamental science, we have developed equipments. From that equipment, because of the curiosity that we want to develop an equipment, we developed an equipment and then we studied the nature. So that will lead to further development in designing new techniques and things. Hence, the basic science is the background for any applied science. But basic science requires a lot of time before it gives us any application. That is what I was talking to your secretary this morning, just a while ago, that I told her in science, in scientific research, it is not overnight. Sometimes it is overnight, but the overnight great discoveries come through systematic investigation for a very long time. This kind of basic science is called blue sky research. This blue sky research takes a lot of time. People might tell you, what is the use of making this compound and throwing it to the sink? No, it is not that. The new materials which are produced in the laboratory might be applicable few years later. That is why I said the basic science, the blue sky research needs lot of time before it becomes an application. Now, I will give you a solid example for that. For instance, the first idea of laser was given by Einstein. I don't know how many of you know. It was in 1916, 1916. It took 44 years between the basic discovery and the first laser. That was in 1960. You know, 1916 to 1960, 16260, 44 years. Look at it. The basic scientific discovery was done in 16 and it took 44 years to come out with the application. The real laser was produced after 44 years of its discovery. So hence, my dear youngsters, don't feel bad if you are taking a fundamental research in basic science. That fundamental research in basic science will have its application after a few years. It takes time. Even though it was found by Einstein in 1916, it took 44 years. So if we do basic science research, you will be known later. So also, you can, in fact, I just skipped one page and then come back to it. Now, I shall come back to the three fundamental scientific units, namely atom, byte, and the gene. I want to give you a little bit explanation on that. Looking at them is very similar to looking at a sentence. What is a sentence? Sentence is a combination of words. Each word has a meaning. Unless otherwise you know the individual meaning of a word in a sentence, you cannot understand the meaning of a sentence. You got my point now? So if you want to understand the technology, the product, it is like a sentence, and the atom is like a word. So unless otherwise individual words' meanings are known, it will be difficult to understand the meaning of a sentence. This is exactly is the relationship between science and technology. It is the same for the matter of an atom, information for the byte, biology for the gene. Hence, the atom, the byte, and the gene provide fundamentally new scientific and technological understandings of their respective systems. So these tiny units represent the respective big units. You cannot explain the behavior of matter, why gold gleams, why hydrogen combines with oxygen without invoking the nature of matter. Without invoking the matter of matter, you cannot be able to say how hydrogen can burn with oxygen to form water. So also, you cannot understand the complexities of computing, all kinds of interface without understanding the byte. And alchemy could not become chemistry until the fundamental units were discovered. Alchemy, people know, people thought, when I heat some other metal with iron at a high temperature, I can get gold. Mad people were there. They were the alchemists. But you cannot make a metal by melting with another metal. You can make an amalgam or an alloy, but not another metal. That understanding came when we knew there is a specific atom. That atom has got particular number of neutrons, electrons, etc. That is different for gold and that is different for iron. So you cannot make. So that kind of alchemy could not become chemistry before we understood the nature of the atom. So likewise, without the understanding of the gene, you cannot get perfect information. If now, in fact, my dear youngsters, the knowledge in basic gene technology is so much that we no longer alter the genes on test tubes in the laboratory. You can alter them in real human being. You can really find out the cause for a particular disease. If it is due to the particular gene, the defective gene can be replaced by a healthy gene. That kind of technology has already been developed now. Look at. If that is the kind of technology that we have, that means if you can replace a damaged or defective gene with a healthy gene, look at the development that we have got on gene technology. That is why I said, my dear youngsters, whether you take up your higher studies in basic science, mathematics, physics, chemistry, and biology, it's very important to know these three tiny units very clearly. Now, the other point that I would like to tell you is, don't think that you may not be able to contribute to the society by your scientific research. I shall tell you how few Indians have really made remarkable discoveries so that their names are there forever. I tell you, their names are there forever for the basic scientific discoveries that our Indian elders have done. You know, Raman, Raman effect, Raman spectroscopy, an additional spectroscopy for a year. You know, Raman, after his BSc honors in physics from Presidency College, Chennai, he was given a job in an accounts general office in Calcutta. He was a clerk. Being a clerk, he was not satisfied. His passion for science was so great that he approached the University of Calcutta to give permission to work in the laboratory after 5 o'clock. 5 o'clock his office work is over, then he got an permission to work for his scientific discoveries in the laboratory. He was given permission. He was doing it. He was measuring the IR spectrum of many compounds, simple IR spectrum, many compounds, till up to 12 o'clock, midnight or 1 o'clock, and then he used to go home. Then he will start his work in the morning in the office and comes to the laboratory in the evening. One day, if you know the spectroscopic IR technique, there is a source, you have the sample here, and there is a coniometer. When you pass the IR radiation, it passes through the substance, it absorbs some kind of a radiation, and the rest is left out. It is being measured. That is given in the form of a spectrum. And you understand what is that vibration, what is it due to, and all that. He was doing it frequently, routinely, for all these days. One day, this coniometer should be fixed with a screw on this side. Fortunately, on one day, he forgot to screw that, so the coniometer was loose. So because of the wind from the window, the coniometer, instead of saying it here, it was at 90 degrees. It was pushed to 90 degrees here. So when he came in the morning or the next evening, he found that the coniometer at 90 degrees, and he got strange absorptions. Not like what he was observing right here in 180 degrees, but at 90 degrees he got a different absorption. He analyzed, and that is what is the birth of Raman spectrum, Raman spectroscopy. Okay, so what made him to discover this? It is the passion for science. He was not satisfied by doing a clerical work. He satisfied his scientific instinct. Then he was able to, now there are n number of spectroscopic techniques. Raman that, Raman this, Raman this, Raman that, so many spectroscopic techniques based on his discovery. Now, believe me, youngsters, you could be one like that. Now, I will give another solid example to motivate you. I said, you could be one like Raman in your lifetime. Why not? And Raman could achieve it so many years ago with all these, facilities you have at your desk and the laboratory. You may be able to produce much better things than him. Now, I will give another example. Sit back, please sit back and relax. Take a deep breath. You take a deep breath. What happens? You inhale air. The air contains oxygen. The oxygen goes to the lungs, and that oxygen is being taken up by the hemoglobin in the blood. Hemoglobin is an ion complex. There are 5 nitrogen atoms from tetragonal ring systems, iron, 4 coordination. Then the 5th one is for sulfur from methionine, and then the 6th position is vacant. That 6th vacant position coordination site, it is where the oxygen goes and sits. It forms a coordination compound. 6th coordination site. That oxygen which is taken up by the hemoglobin is transferred through the flow of oxygen to all the parts of the body where it is delivered to myoglobin for any kind of oxidation. For any kind of oxidation, you need oxygen. And there, while doing the oxidation, this oxygen gets reduced and then it forms water by taking 4 electrons. In addition to that, it produces during that oxidation, while oxygen is getting reduced, there is a product which is called ATP which is produced, adenosine triphosphate. This is the source of energy for our body. So when oxygen is taken up by this hemoglobin, by our inhaling of the air into the system, then that is being used for producing the energy in the form of ATP, adenosine triphosphate. You know, my dear youngsters, who discovered this? It was one Dr. Subbarao from India in 1960s. You will be surprised. That Dr. Subbarao, this will be another example there, should be able to motivate that by doing routine research work, you may be able to get a wonderful thing. In fact, Dr. Subbarao was a medical doctor. In 1960s, he went to USA from Andhra Pradesh to find a job as a medical practitioner. At that point of time, there were a lot of restrictions, rules and regulations that he could not get a medical professional job. So a biochemist, a biochemistry professor, employed him as a researcher to routinely purify the proteins. You know, he was trying to purify the proteins in his work. So he was given a technician's job, though it is scientific, but it is a technician's job to purify the proteins. He was routinely doing it for many years. Ultimately, it was he who found the ATP. During the course of the systematic investigation in purifying the proteins, he came across the ATP. Now, believe me, my dear youngsters, had he been an American, he would have been given Nobel Prize in 1960 itself. But unfortunately, he was not given. He was not very well recognized for that discovery. What I am trying to say here is that sometimes you may be able to produce great things, but it might go unnoticed. But that should not be a reason for getting discouraged. Be bold that in the end, I will be able to do something. And if you feel satisfied by doing something in your work, that is great. So this is the second example wherein an Indian has done wonderfully well. Very recently, I will take a few more minutes. Okay. Very recently, you might have read in the newspaper that NASA, American agency, has flew the first powered and controlled flight on another planet, not on Earth, on another planet. On this planet, who flew the controlled flight? Wright brothers. In 1903, Wright brothers flew the first flight. You know, it did not go very well. First, there was an accident, a man died, but still that did not prevent the Wright brothers to go ahead without the difficulties, without, worrying about the difficulties. They went on to find the flight. That is why we could fly now. Now, like that, the first flight on another planet was carried out by NASA USA. It is called Ingenuity Mars helicopter, which was sent by NASA successfully, which took off to Mars and landed there safely. This is the first ever powered and controlled flight on another planet. The US Space Organization hailed this achievement as that of Wright brothers, as I mentioned, who flew the first flight in 1903. Though this helicopter, which took off and landed on Mars, another planet, to only 3 meters high, and it stayed there for only 30 seconds, it was a great achievement because you could do any kind of flight, taking off and then landing on land, our land. But on another planet, the planet with which you have no pretty knowledge about it, you can send a flight and then it takes off and then it lands back safely. That's a great achievement. This was appreciated by the American government very greatly. And you know, the achievement was done by none other than an Indian called Balram. Now, this is yet another example wherein the scientific interest and the routine research can lead to technological development. Look at the way the Indians have contributed to science and technology. All these things point out to us only one thing, that we need advanced materials for better technology. So, my dear youngsters, since most of you are chemists, take up some fundamental basic research with the understanding that I have mentioned earlier about the atom byte and gene. If you do systematic, serious research on your chosen area, I am very sure that at the end you will end up with discoveries like this. May not be for all, for some of you. So that some of you can be any one of you in this. Finally, while giving this keynote address for the great international conference organized by this college, I would like to close my keynote address by reminding you, I reminded you earlier, 2 things. Please remember, become an expert and communication in English. Besides that, I have yet another thing to tell you. My dear youngsters, the whole world is looking for youth. What do you mean by youth? Youth, the younger age of people, either a boy or a girl of age 25 and 35, they are called the workforce, youth force, all over the world. You know why? In any Western country, if you have read the newspapers, people live together, they get married, they don't want to have children. Thereby, the population becomes less and less. In fact, these countries, especially Germany, France, Australia, all these countries, they lack youngsters because no parents would like to have a child. Where will the workforce come from? It has to come from outside. In that sense, my dear youngsters, Indian youngsters, you have a very bright chance. Though we are second in terms of population compared to China, the number 1, we have an added advantage I mentioned earlier, that our education is basically in English. So that will help you when a job is offered in comparison to a Chinese fellow, though they are more in numbers. So youngsters, please see to it that you have fantastic future in terms of the job and opportunity to produce new things all over the world, because you have your education in English. That is exactly why I told you, my dear youngsters, that in addition to becoming an expert in your field of research, it is equally important to be good very good in communicating English. So with this few words, I feel it a great pleasure, and indeed I am extremely happy to give this keynote address for the conference, and I wish you to go through the whole 3 days proceedings and see what other people are doing in different areas of science and where you can fit, where you can do something. Before completing, I want to tell you that among the speakers in the list of this thing, there are two of my students. There is one Dr. Natarajan and another, what is his name? I want to. Kanigai Malai. Dr. Natarajan was my student. He did MSc in our department long time back. Then he went to Germany. You know, his idea was to become a big professor. He did another MSc and he did his PhD also in Germany. Then he went to England, Southampton, where he is currently working in a pharmaceutical company. You know, the pharmaceutical company is owned by the professor under whom he worked for research. He made him a partner of that company. Look at, my dear youngsters, one of my students, a very ordinary student, because of his passion to become interest, to become something great in his life, he took all this pain to go to Germany, did another MSc, PhD, and then went to England. His talent was so much appreciated by the professor in England, so that in the pharmaceutical company owned by that professor, this gentleman, Natarajan, is a partner of that company. Look at, he is going to produce wonderful things. Likewise, Kanigai Malai was another student of mine, and after his PhD, now he is a research associate in University of Tübingen, Germany. You know, University of Tübingen has produced half a dozen Nobel Prize winners in Germany. So, such a great thing that these people could achieve just by what? They have the basic interest. All that I tell you is, after going through this seminar, listening to the experts, please have some kind of an interest, create some kind of an interest, so that you do something which will make you known for better. And I thank this management of the college, the faculty members of the Department of Chemistry of PSGR Krishnammal College, for having chosen me to give the keynote address, and I am sure I have done my job. Thank you so much.
Thank you, sir, for the highly informative and stimulating speech, in specific about the tiniest atom, byte, and gene. I assure that our students will rise up to your expectations to the cited examples. Thank you once again, sir. Dr. Bobby Kannan Mathan, Research Academic School of Engineering, University of Newcastle, Australia, has joined us to deliver the inaugural address. I invite you, sir, to share your expertise on the captivating topic, Next Generation Metallic Implants, Fix It and Forget It. Sir, over to you.
Thank you, Dr. Yesodha Devi, for the kind introduction. Good morning to all of you, and thank you to Dr. Natarajan for this inspiring keynote address. Thank you, sir. And I would like to also thank or also congratulate Dr. Selvi for taking the lead in organizing this conference. I know it's very difficult to organize anything for the matter in this pandemic time, and she has brought in some eminent speakers for this conference. Good work. I hope it be a successful one. Also, I'd like to thank her for inviting me for giving this inaugural lecture. I'm deeply honored, and it's a great pleasure to present my research work to the students in particular, and of course to the other audience as well. So the title of my presentation is Next Generation Metallic Implants, Fix It and Forget It. Uh, Believe me, this is a fascinating subject, and it's a hot topic as well. I'm currently associated with the University of Newcastle, but this work started long ago, more than 10 years ago. Uh, Let me give you a brief introduction to how I got into this fascinating topic. My interest in this area started when I joined a Helmholtz Center. Sorry, this is, yeah, sorry, yeah, yeah. Uh, my interest to this very subject started when I joined this institute in Helmholtz Research Center. I worked there for a couple of years. I'm sure most of you might know or heard of Alfred Nobel, who created the Nobel Prize. And in fact, he worked in this institute and he invented a dynamite in this institute in 1867. It's a very famous institute, and now it's very famous for its magnesium research work. They develop all kind of magnesium alloys, starting from A to Z. Magnesium being a very light metal and the lightest engineering metal available. They develop alloys for automobiles, aircraft applications, and recently for biomedical application as well. During my time, I did some work on advanced magnesium alloys, uh, basically looking at the failure of material, particularly when we talk about high strength materials, they are prone for cracking. So I looked into how these advanced alloys cracks and how to mitigate that. And that is where I got interested in this material, the lightweight material, came to know about their properties and their fascinating properties. So when I moved to Monash University, I started this work on this magnesium-based biomaterial applications. Uh, I was one of the first few to start this work on this topic. And after joining JCU as an academic, I continued to work on that. And most of that work I'm presenting today was done at James Cook University in Queensland. Right. Going to the topic, bone fractures. Bone fractures are very common. Millions of fractures are recorded every year. A statistic says that globally in 2019, there were about 178 million fractures have been reported. I'm sure there are many more which has not been reported. Not only the numbers or number of fractures are high, but there's an increasing trend in the number of fractures as well. This is due to a few things, particularly the aging population, especially in the Western world, and deficiency in calcium and vitamin D deficiency in the humans. And surprisingly, it's also contributed to the increasing number of accidents on roads as well. So in Australia, it's been said that a bone breaks every 3.4 minutes, which accounts for about 150,000 fractures a year for a population of 25 million people. That is extraordinarily high. And the situation and the annual cost is estimated to be about $2 billion. Uh, and it doesn't look better. In fact, it looks much worse for India. Looking at these data, it's reported that Indians have around 15% lower bone mineral levels than Westerners, and about 80% of the urban Indians are vitamin D deficient. So no surprise, you see these kind of supplements, calcium and vitamin D, supplements in the supermarkets. So the number of fractures in India is not recorded, but you can imagine, if it's 150K in Australia, it should be much more in India. So what happens and how is these bone fracture treated? When the fracture is very minor, otherwise called as hairline fractures, they don't need any intervention at all. However, major fractures require a surgery. This is an old statistics which you can find here that was done in 2003. It was reported in the US alone, it's close to 1 million fractures requiring surgery, and Germany 500,000, and close to 100,000 in Australia. This was in 2003, so I'll not be surprised that this might have doubled by now. So the treatment for these fractures involves realigning the fractured bones. They realign the fractured bones, and they are held together using plates, screws, and nails, as shown here. This is one of an example where this is a long bone fracture where the screws and plate is placed, and the screws are used to hold them. And this is another example of a maxillofacial fracture. And it's quite common in Australia, where they play these contact sports called rugby, and quite often you see players undergoing, treatment and for maxillofacial fractures. So what are these materials? What are these materials made of? Currently, the materials for those mini implants are stainless steel, cobalt, chromium, and titanium-based alloys. If you leave these materials for a longer period of time, there is a risk for local inflammation. It can undergo wearing. Wearing means rubbing of the metal to the bone, and can cause debris of metal particles, which can be very inflammatory. And also leaching of ions also can lead to failure of the implant and causing inflammation. And in addition, there are some dissimilar mechanical properties to the natural bone. So if you look at this table here, the properties of these conventional, so-called conventional alloys, titanium, chromium, cobalt, and stainless steel, they are quite different than to the natural bone. Especially focus on this elastic modulus, they're quite high. So when there is a mismatch in those mechanical properties, this will lead to what an effect called a stress shielding effect. Stress shielding effect, it will delay bone healing. It doesn't naturally heal. So it is quite undesirable. And so what is the conventional route is here is for these mini implants, after the surgery is done, the implants are removed, right? A removal of implant, meaning that there is a risk. Any surgery has a risk. Okay? There's a risk to the patients, and also it adds to the cost to the patients, and a burden to the healthcare system, especially in the Western world. It's quite huge. To make it worse, when the implants are removed, it can leave these kind of holes in the bone, okay, and it can also refracture. That's the worst case scenario you could have, right? So just to give you an idea of what kind of problems these these so-called permanent implants cost, even in what you call, where permanent implants are required, say in the case of total hip replacement. This is slightly out of topic, but I'm just trying to give you the gravity of problems caused by these implants. um, Arthritis Research UK, they report that 1 in 10 THPs requires revision THPs. This, one of the main reason is wearing of implants causing the debris of particles, right? And in fact, not long ago, over 1,700 Australians were affected by cobalt chromium toxicity. That's again a hip replacement implant due to metal degradation from HPs. Okay, so we don't have an option. We have to use this material, but research is going on in improving the properties of them by biocompatible coatings and so forth. But do we need these materials for mini implants? Because we don't need a degradable implant, right? So typically for mini screws and pins, the service life we are looking at is 3 to 6 months. It again depends on the severity of the fracture, age of the patient. So we don't need a long-term implant like this cobalt, chromium, or stainless steel or titanium-based alloys. What if you have a material that can slowly degrade, right? Slowly degrade as the bone heals and disappear. I mean, it sounds fascinating, isn't it? And you can call it biodegradable implants, right? Here, this is just a cartoon of what I was talking about with non-degradable implants. What happens? You might need a second surgery to remove it, and refracture is a possibility. But if you have a material which can slowly degrade and disappear over time, then you could avoid these scenarios, and you end up in having a complete healing. That's why I call it fix it. You fix the implant and then forget about it. You don't have to worry about any revision surgery or causing any toxicity or anything like that. Are there materials which can do this job? Biodegradable materials. Actually, biodegradable polymers are there. They have been there for over 10 years or more, if not, which can degrade in body fluid. Polymers like PLA, polylactic acid, and polyglycolic acid, and its co-polymers are available. They are biodegradable, and their products are easily excreted in the urine. They basically polylactic acid. It breaks into lactic acid, which is naturally found in milk. So the biocompatibility is also good with these polymers, and FDA has approved many of these biodegradable polymers. And in fact, they have been used in sutures, biodegradable sutures and mini implants, where you don't need much of a what you call load-bearing capacity. But for orthopedic implants, which my group is focusing on, um, we need a material with a high strength. If you compare the mechanical properties of a natural bone and this polymer, it's quite low, right? You can look at the compressive strength is quite low. Elastic modulus is on the borderline. So uh, we need a material with a better strength, okay? And when talking about strength out of these classes of materials, I would pick metals. Metals have better strength. You could work on it. You could tailor the properties. You can alloy it. So there's so much you can do with metallic materials. So that's how we got into this magnesium metal. Magnesium metal. It's a lightweight metal. It's a lightweight, and as I said, it's a lightweight engineering material available. So its mechanical properties good. Um, it's biodegradable. I mean, magnesium in a body fluid can dissolve, and it is biocompatible. It is actually necessary for our human metabolism. It is an essential nutrient, and similar to calcium, which we know it's required for bone growth. Magnesium also stimulates bone growth, and will they and it's non-toxic, right? This no scenario of hypermagnesium. What I mean is, you can't overdose yourself with high magnesium, because magnesium dissolution, if you look at the mechanism here, magnesium form in water. Basically, body fluid has a lot of water in it. That's how it reacts. It forms a magnesium hydroxide, and the magnesium hydroxide, in the presence of chloride ions, which body fluid has chloride in it, it forms a magnesium chloride, which is soluble in aqueous solution. So there is no secretion of magnesium in the body. Even if you overdose it, it's easily excreted. But yeah, that's the reason why even you have this dietary magnesium available in supermarkets for treating cramps and sleeping disorders. And as I said, the properties is also quite close to that of natural bone. Particularly, what I'm talking about is this stress shielding effect, which is important when you talk about orthopedic applications. That's pretty close to that of the natural bone. So why not use magnesium as an implant directly? Unfortunately, there are some hurdles. There are challenges. There are two major challenges. The first challenge is the degradation rate. The degradation rate of magnesium is too high. It's extremely high. See, we are talking about a metal to degrade, but it has to survive for that period. I'm talking about 3 to 6 months. But this dissolution is too high, about 22 millimeters per year. To just give you an idea of what it is, in fact, you could uh, glow a bulb by using magnesium degradation. What I mean is, magnesium is dissolution is an electrochemical reaction, right? You have an anodic cathodic reaction. You can form a battery out of magnesium, a rod in an aqueous solution, and you can blow a bulb there. It is that high. And in fact, in recent years, there's been work going on magnesium batteries as well. Uh, with this rate, the implant will dissolve before surface light, right? And it can't withstand the loading during that period. The second problem, which is associated with the first problem, is because of the high dissolution, degradation rate, they produce a lot of hydrogen, right? As I said, it's a electrochemical reaction. Magnesium dissolves and hydrogen evolution happen. So the more the magnesium dissolving, higher the hydrogen. So these small hydrogen bubbles, they coalesce, they come together and form a big pocket near to the implant. Okay, when you have such pocket of gas, it is difficult for the bone to heal. There's no contact between the body fluid and the what do you call the implant and bone. So bone healing is delayed by that process. In fact, I was talking to a scientist, or in fact, he's an orthopedic surgeon and a scientist, Frank Witte, about this hydrogen gas forming. He said you prick a pin, and you can remove the gas. It's a funny side of him. So it's that big, I mean to say. So how do we overcome these challenges? Especially the degradation rate. If you could control the degradation rate, you could control hydrogen, and thereby you could use this material for implant applications. Uh, Generally talking, when you talk about metals like mild steel undergoes severe corrosion, right? And people have added chromium and nickel to that to improve their corrosion properties, and that's how the invent of stainless steel has come in mid 90s, right? You can't think of a world without stainless steel. Pharmaceutical industries, or food processing industry, or even chemical industries. Without that highly corrosion resistant stainless steel, it is hard to manufacture or produce high purity products. So a similar approach can be used for magnesium as well to control the degradation. A lot of work has been done. As I said, magnesium is not new. It's been researched and used for engineering applications. So some of the alloys are aluminum, zinc, niobium, ytterbium, and to some extent calcium as well. So there are magnesium alloys with these combinations. And unfortunately, uh, alloying of magnesium is not as simple as in steels because of its highly reactive nature. And alloying is done at a very high temperature at its melting point. We are talking about 660 to 670 degrees centigrade. So when it is exposed to air, it will just catch fire. So you have to do it in an inert environment. And the solubility, when you do alloying, you can't just add XYZ into it. You have to understand the solubility of these ions as well. And mostly these magnesium has less solubility to with these elements. So there is it is narrowed down to only a few elements which I've highlighted here. Uh, Aluminum containing magnesium is quite popular for engineering applications, but as you know, aluminum is known for or reported to cause Alzheimer's disease. So there is some hesitancy in going for AZ series alloys. And talking about this other rare earth elements, ytterbium and niobium, the toxicity of these elements are not well understood. However, to start with, we did work on these aluminum containing and rare earth containing alloys because there was no literature available. And as I said, we were one of the first to work on these type of alloys. This slide, this slide, uh, we did a series of tests on different alloys, and I'm just showing you only a few of them here. We started with a well-known AZ series alloys, which is of this is a sand cast and die cast. It's the way they make the alloy. You don't have to worry about that. This one is later on we studied adding calcium to it. Now, calcium is biocompatible. We know that bone is the one of the major component is the calcium. So we add calcium to see that and see whether it influences or controls the degradation. And also, as I said, we looked into the rare earth elements as well. So, in a nutshell, what I could say from this slide is alloying improves the degradation resistance to some extent, but it's not sufficient enough. And more importantly, I'll touch upon two things. One is this. Look at this. This is a sand cast alloy. This is a SEM picture after the degradation testing, and you see these large pits there. These pits. That means the degradation is not uniform. It's a non-uniform, localized. We don't want these kind of degradation because these type of pits can cause a local failure. This can act as a stress riser when there is a loading, and it can fail catastrophically without any warning, which is quite dangerous. And the second one is the die-cast alloy. Here, this one, although it is aluminum zinc magnesium alloy, the picture you're seeing here is mainly an intermetallic. It's intermetallic. The magnesium is dissolved and left behind this skeletal structure of beta phase. We call it. It's secondary phase particles. What is secondary phase particles? When an alloy is done, when it reaches a solubility limit, they form a compound that's called the intermetallics. We call it. It's in this case, it's a magnesium aluminum intermetallic. The problem with this is if we use these type of alloys, what happens to these intermetallics? Whether it's going to stay there, it's going to dissolve, or if it breaks into small pieces, it reacts with the cell. It can cause a process called necrosis. Death in cells. So we need to understand how these intermetallics behave, because you can't avoid intermetallics in magnesium alloys. Perhaps this slide shows you the number of alloys available, one of the top popular alloys here, and you can see all of them have intermetallics, right? So it is very critical to understand its behavior. We know magnesium dissolves, but leaving behind these one will cause much more complex problems. So we wanted to study this, how this behaves. So what we did was we we created what we call the secondary phase particles. I said producing a magnesium alloy is difficult. Producing secondary phase particles is much more difficult. So this was done in collaboration with Karabuk University in Turkey, who are specializing in what do you call these intermetallic particles manufacturing and producing. So a student, a PhD student from that university visited my lab with this sample that's intermetallic, and we did some testing on those alloys. Uh, as expected, the intermetallic was quite noble to that of the matrix. So the matrix is magnesium, pure magnesium, which has a very highly negative potential, and your beta phase is quite positive. So if this dissolves, and that is protected. So what we did was we clubbed together, we joined together to see the galvanic effect of these particles. Galvanic effect of these particles. We did it using an electrochemical setup. We connected a zero resistance ammeter and measure the current produced from this. Interestingly, it was not a smooth curve, right? You see some a pattern, a cyclic pattern of high current and low current. A closer observation of those samples revealed that there is some bubbles forming on the samples. Okay, in one side the magnesium slowly dissolves, and the other side there's bubble forming on top of the beta phase particles. We took that to analysis using SEM, and as you can see, magnesium dissolution was uniform. It was good. It was pure magnesium, by the way, and this was the beta phase. And on the beta phase, we didn't expect it to dissolve, but it formed a product on top of that. And the analysis of the product using FTIR and your excited analysis showed that it's kind of an amorphous phase. It's composed of calcium and phosphate, suggesting that it's a calcium phosphate deposition, because human body fluid has calcium and phosphorus in it. So it formed a calcium phosphate, and I was talking about the hydrogen bubbles forming. So these holes left behind that suggests that the bubbles are formed, and it is escaped from the thing. So it was worrying that why is this protecting? Why is this protecting? If this is protecting, then it is going to be much more detrimental. But we took that sample and separately analyzed how it behaves over time in body fluid, and surprisingly, and it's good news that although the resistance of this beta phase at the initial stage was quite high, this is a base metal, pure metal. The dissolution is fast, is high. It started to decrease over the period of time, which suggests that these beta phases are not highly stable. It dissolves over time, although it is slower than magnesium, dissolves over time. Otherwise, we can't use this material for implant applications. So we proposed a model, the formation of calcium phosphate, dissolution of the alpha phase, forming of what you call the calcium phosphate, and how the calcium phosphate dissolves. So there are about 6 stages, and it goes around. It's a cycle. So ultimately, at the end of the day, your whole alloy is dissolved, right? So that's good news. But as I said, the localized degradation is a problem. Localized degradation problem, because that can affect the mechanical integrity of the implant during service. So what next? We have done alloying. We could do the best we could, and so we looked into the next stage. The next general method for improving the degradation resistance is coatings. So we worked on some coatings. Coatings are not new for implants. Even the permanent implants, which I was talking about, the titanium based for long bone and things like that, they have this robust coating known as zirconia coatings and titania coatings, right? And there are various methods to coat implants, like spray coating, plasma coating, dip coating, and electroplating. But these coatings are not suitable for temporary implants because they are very robust coatings, right? We don't want highly resistant coatings. We need something it'll dissolve over time, right? But it should be better than magnesium. We look back into the polymers, which I talked about, this PLA, PGA. These polymers, they are biodegradable. They're biodegradable. They can't be implant by its own, but as a coating, it could serve some purpose. So for its biocompatibility and low degradation rate as compared to magnesium. We looked into two types of coating. First is the dip coating. Uh, the dip coating produced a thick coating, a very thick coating. Because of that thickness, what happens is the adhesion of that coating to the metal was quite poor. So we had to rule out that, and we went on to do a spin coating, where the solution, the polymer dissolved in a solvent, is dropped onto a disc, and that's how spin coating is done. It produced a relatively thin coating, which is what we were after, and the addition was quite good as compared to the dip coating. These are some of the results of a spin coating of polylactic acid. Uh, Here, as the thickness of the coating increased, the resistance also increased. But very high resistance also was not desirable because of this degradation mechanism of polymers. It's undergo a process called bulk erosion. It's not the surface erosion; it's a bulk erosion. So since it's a bulk erosion, higher the coating, the permeation gets into it, and the thickness plays a role, and the bulging of the coating occurs. So we have to optimize the thickness of the coating. So here we looked around 2 to 3 microns were good enough to withstand what you call the resistance, and also to provide some long-term what you call protection. Next, we worked on other materials as well. In addition to the polymers, we looked into material called calcium phosphate. Calcium phosphate is naturally present in a bone, and it is present at what we call as hydroxyapatite. It's a form of calcium phosphate. It's highly biocompatible. It's an inorganic compound, and of course, if you have calcium and phosphorus, it will accelerate bone growth. There are different coating methods. There are high temperature methods, which are normally used for these permanent implants, this titanium, cobalt, chromium alloys. And there are also these electrochemical deposition methods, which is much more useful for magnesium alloys, because you can't take magnesium to these high temperatures. We're talking about 1,000 degrees centigrade, whereas magnesium melting point is quite low. It's about 670 degrees centigrade. So our only option was to go for electrochemical deposition. And there are advantages. You can coat complex shapes, which is very important, right? Because your implants are of irregular shape, so you have complex shapes as temperature low processing temperature. You can control the thickness by altering the voltages, current, and also tailoring the electrolyte of the coating solution. And it's quite simple and inexpensive. So we did some coating, calcium phosphate coating on magnesium, on pure magnesium. But surprisingly, we saw that the coating adhesion was very poor. Very adhesion. As you can see, this just a photo of coating on a magnesium alloy. You see these particles falling down. The coating is not adherent to the coating, to the sample. Unlike in other materials like nickel plating or zinc plating, they are quite very adherent. But in this case, they are not adherent. It is falling down. Again, the hydrogen evolution reaction is playing a role there, which causes the coating to break and fall down. Right. So what we did for the first time, we did to control the coating kinetics. We thought let's increase the resistance. In other words, increase the resistance. In other words, decrease the conductivity of the electrolyte. So we used an solvent, ethanol, this volume percent, and measure the conductivity. As expected, the conductivity decreases with the increase in the ethanol content. And we did some coating. As you can see here, the coating thickness has decreased with the increase in the ethanol content, which is expected. But more importantly, look at the morphology of the coating it has produced here, where with an aqueous only solution, you have this what you call porous structures. And as we say, having a coating with porous structure is worse than not having a coating, right? So you don't want these kind of morphology. And with the addition of ethanol, it created a much highly dense packed coating in this case. Yeah, and the resistance is also high, right? High. Sorry, how many minutes do I have? 10, 15 minutes? Is it okay? Okay. Yeah. So
You can take up 10 more minutes.
thank you.
Yeah.
So we did, as a next step, we further controlled the the conductivity of the the electrolyte and the kinetics by using ethanol and a technique called pulse potential, and we created a very flat, dense coating. Okay, it's one of the highly resistant coating. We did some biocompatibility testings on those coatings. We took this, I visited NIMS, it's an institute in Japan. We did some biocompatibility testing. These coatings have produced quite good biocompatibility, which is a good news. The next coating we looked into is an advanced coating. It's called a plasma electrolytic oxidation coating. I don't have much time to get into the details, but what I want to say is these coatings produces a porous structure. It produces a very hard surface, but it causes a porous structure on the material. So what we did was it forms a thin layer, adherent layer, and a porous structure to we seal those pores using polymers and calcium phosphates. And see, this is a slide showing a polymer coating sealing those pores, and the resistance is pretty high in this case. And we also did some calcium phosphate coatings on top of that, and similarly, that also showed some high resistance. Yes, you can see the difference in the resistance provided by this coating over a period of time. And the initial resistance is much more important, although it is for 3 months or 6 months. The initial resistance is very important. And we also ended up in having for the first time, we created a triple layer coating involving all the porous structures, calcium phosphate deposition, and the polymer. And this result, is the highest resistance ever produced for this material, right? And we recently published in Medical Devices and Sensors. Quickly, I want to touch upon one other topic, is the mechanical integrity. It's very critical to look into the mechanical integrity because we are talking for orthopedic applications. The implants undergo various modes of stresses, and when the stress is combined with a susceptible material, they can cause cracking. And particularly when I showed before, when there is a pitting, this can cause failure. See, even the permanent implants can cause failure, so let alone these biodegradative implants. There are various techniques, very quickly, there are various techniques, fracture mechanics approach, low strain testings. We looked into all of them, and we proposed, I don't have time to talk about individually, but we proposed that circumferentially circumferentially notched sample is an ideal specimen for testing these kind of samples, because generally this mechanical integrity is done using a smooth specimen. Okay, the index is quite high, and you need a low index. The testing by testing you need a low index, but actually you need a high index for better integrity. But in testing you need a low index. So this one circumferential notch sample is a better, and ideally we would like a fatigue crack, but it's much more expensive to do that. So we propose that circumferential notch is the best sample. Uh, and so there's some ongoing research. I've established collaboration with this Chinese institute, and I visited them a few years ago. And we're looking at a series of tailoring the calcium phosphate coatings by adding bio-inspired molecules, loading with critical molecules for biocompatibility, antibacterial property, and adding nanoparticle of silver and so on and so forth, which I'm not going to discuss right now. So, in conclusion, I can say that the degradation rate of magnesium can be effectively tailored for biodegradable implants. Allowing is beneficial but not sufficient. Hybrid coatings are essential, and it's promising. And mechanical integrity evaluation is critical for these successful implant applications. Quickly, I want to talk about the other research I'm doing in my lab. One is the zinc-based materials, which is similar to that of magnesium. We were the first to develop a porous zinc material for this biodegradable implant applications. It has all these beautiful properties, and in fact, the degradation rate is lower, but it has other complications, toxicity complication, which if you're interested, you can read these publications, and we have details there. The other research, we also work on these permanent implants, titanium-based biomaterials. We have collaboration with a Korean institute, Sochin University, and we develop these new alloys, titanium-based alloys with better biocompatibility and elastic modulus as well, which I talked about, stress shielding effect, which produce low elastic modulus, and surface engineering for better properties. And we published many papers in this area, and this is one of them. And not only on biomaterials, we also work on engineering materials. We work on this fascinating material, nanomagnetic steel. That has a very high strength. Just to give you an idea, if a material requiring, if a mild steel requirement is 1.5 for a particular load, the thickness can be reduced to 0.3 if you use a nanomagnetic steel, meaning that you have a lot of weight saving. Say, for example, you have a car, you replace the mild steel by nanomagnetic steel, you have a weight saving of 80%. And we're looking into their application in oil and gas industries and their failure mechanism, and so on and so forth. And we published a paper recently in these journals if you're interested in. And if you're interested in any of my other work and the work I presented, you can hop onto these Google Scholar and find me there. You can see my list of publications there. You can follow me on ResearchGates or Mendeley, and also look at Scopus site. I'd like to acknowledge my collaborators and the sponsors who have funded me. Without their support, it would not be possible to do these research works. And finally, I would like to thank my lab members, Biomaterials and Engineering Materials Laboratory. We had a what do you call? It is a truly international group. We had students from all around the globe, around 15 from 15 different countries, and quite enthusiastic in doing work. And with that, I end my talk, and thank you all for listening, and I'm more than happy to take any questions if you have. Thank you.
Thank you, sir, for the insightful lecture, highlighting Nathan's advancements in bone fracture treatment, repairing surgery, current implants like maxillofacial PHPs, they are biodegradable and biocompatible nature, and how to overcome the encountered challenges. Participants can post their queries in the chat box and shall also unmute themselves to clarify their doubts. Yes, we have one question here, sir.
Sure.
Thank you for the wonderful presentation, sir. I have one question. Can metal implants cause the autoimmune disease in our body?
So, sorry, I didn't get your question.
Sir, can metal implants can cause any autoimmune disease in our body?
No, magnesium. Metals can. Metal can. In generally, metals like cobalt, chromium, or those kind of metals can. But magnesium is quite highly biocompatible, right? And it is biodegradable as well. As I said, you have a very limited chance of hypermagnesium. No, it easily excretes through the urine. So the complication due to those metals is very rare, especially for magnesium alloys.
Okay, sir. Thank you, sir.
Thank you, sir. I have a question, sir.
Yeah.
Sir, is bulk erosion and thickness of coating is related, sir? Upon
Bulk
increasing.
erosion. Yes. See, bulk erosion is certain polymers are bulk. The erosion is bulk. Bulk means that it's not only the surface erosion, right? PCL, polycaprolactone, it's a surface erosion. We would prefer. I mean, there's two sides. If you have a surface erosion, right? Surface erosion, your material below is protected, but you have to wait until the complete polymer, in the case of PCL, has to dissolve, and then the magnesium is exposed. Okay, but if you have a bulk erosion one, it's the dissolution can occur simultaneously. Initial, the dissolution occurs in the polymer, and as the electrolytes permeates through, the polymer also degrades, and as well as your metal degrades. So there's a confusion. So there's an advantage and disadvantage. So in the case of a triple layer coating, which I talked about, we found something interesting there. I don't know whether I have a picture there. Triple layer coating. Here you go. So because here, because the erosion is a bulk erosion, you can alter the porosities of these polymers, and you could tailor it. Custom made. It can be custom made by altering the porosities in these bulk eroding polymers, so that you can say this implant, which this polymer thickness can sustain for a few weeks or a few months. Okay, so that's a big advantage of having a bulk erosion polymers. In the case of surface erosion polymers, you need to have a very thin layer, because you don't want the sample to be there for a longer period of time. So yes, to answer your question, yes, it does affect the service life of the implant, whether it is a bulk or your surface erosion.
Thank you, sir. And another question. How
Yeah.
metal became acceptable by the body?
Sorry, I didn't get your question.
Sir, how metal can become acceptable by the body?
Acceptable.
Acceptable, sir.
How the metal can become, no, it's not acceptable in the sense it is an ion, right? It's not present as a metal. Magnesium, when it dissolves, it is Mg2 plus ions. Okay, it dissolves in the body fluid. It naturally dissolves in the body fluid. So there's no question of of a foreign body present there. Okay, if it is if it is a metal by itself, right? It is difficult to integrate, but it forms as an ion. It is easier for them to excrete.
Thank you, sir. Thank you for joining us amidst your busy schedule. Thank you for accepting our invitation and gracing this occasion. Thank you once again, sir.
It's a great pleasure. Thank you very much.
Thank you, sir. I invite Dr. E. Kayalvizhy, Assistant Professor, Department of Chemistry, PSGR Krishnammal College for Women, to propose the vote of thanks.
The roots of all goodness lie in the soil of gratitude. Good afternoon to everyone connected to the International Conference on Chemistry, Frontiers and Challenges. It's my privilege to propose the vote of thanks on this occasion. With a deep sense of gratitude, I thank our chairperson, Dr. R. Nandini, and our managing trustee, Shriji Rangaswamy, for their constant support and encouragement. I express my profound thanks to our secretary, Dr. N. Yesodha Devi, for her warm welcome and unwavering words of motivation and encouragement keep us steering towards our endeavors. I take this opportunity to thank our principal, Dr. S. Nirmala, for her guidance and support in organizing this conference. Sincere thanks to Dr. K. Natarajan, former professor and head, CSIR Emeritus Scientist, Department of Chemistry, Bharathiar University, for enlightening all our minds with this thought-provoking address on the importance of communication skill, basic sciences and technology-wise, atom, byte, and gene, systematic and innovative scientific research for the technology breakthrough and for the benefit of the society. Sir, your talk will surely pave the way for the source of novel and application-oriented research. Our heartfelt thanks to Dr. Bobby Kannan Mathan, Research Academic, School of Engineering, University of Newcastle, Australia, for supporting us to organize this conference in association with University of Newcastle and for his valuable insights on biodegrade and biocompatible metallic implants for fixing various ailments. Sir, we look forward for your continuous support in the future as well. We express our gratitude to all the resource persons for accepting our invitation to share their expertise and empirical research on the forthcoming days. Our thanks are due to Dr. A. Shamita Begum, Dean Academic Affairs, PSGR Krishnammal College for Women, for her motivation and scholarly guidance. We are thankful to the deans of various capacities, PSGR Krishnammal College for Women, for their constant support. We thank Dr. P. Meena, Vice Principal and Head, Department of Physics, PSGR Krishnammal College for Women, for her gracious presence. I express my gratitude to Dr. D. Nalini, Head Department of Chemistry, PSGR Krishnammal College for Women, and all our faculty members for their unflinching support and coordination. We appreciate and congratulate the organizing secretaries, Dr. G. Selvi and Dr. G. Satya Priyadarshini, Department of Chemistry, PSGR Krishnammal College for Women, for their meticulous planning and efforts in arranging informative and resourceful lectures in this conference. Special thanks to all the delegates from various parts of the country for their significant presence and our students for their involvement and participation in all our activities. We hope and wish this conference will prove to be prolific and beneficial to all the participants. We wish to thank our technical team for live stream the conference and non-teaching staff for the logistic support. Stay safe, stay healthy, and above all, stay positive. Thank you.
Thank you, Dr. Kayalvizhy, for the respectful gratitude. We have come to the closure of the conference inauguration. Participants are requested to stay connected. Technical session 1 will commence now. Thank you one and all for gracing the inaugural session. Thank you.
And we will good afternoon and we welcome you all for the technical session 1. We invite Madam Dr. P. Kanchana, Assistant Professor, Department of Chemistry, PSGR Krishnammal College for Women, to introduce the speaker, Professor J. Shankar, Department of Chemistry, ICCCFC, Bhopal.
Good afternoon to one and all present here. It gives me immense pleasure to welcome and introduce our speaker of the session, Dr. J. Shankar, Professor, Department of Chemistry, ICCCFC, Bhopal, India. Sir did his undergraduation and post-graduation at Madurai Kamaraj University, Madurai, India in the year 1995 to 2000. He obtained his doctoral degree from IIT Kanpur in the year 2005. He worked as Crest Fellow and JSPS Fellow in Graduate School of Science, Kyoto University, Japan from 2006 to 2008. Later, he joined ICCCFC Bhopal since 2009. His areas of research interest include organic materials for optoelectronic devices, fluorescent materials, pi conjugated molecules for NLO applications, near IR absorption dyes, sensors, etc. An added feather to his cap is he has 50 publications in peer-reviewed journals. He has held many administrative positions at ICCCFC. To mention a few, convener member for staff selection committee at ICCCFC. He has around 1,579 citations and his H index is 21 and his I-10 index is 35. Sir, we are fortunate to have such an eminent scientist among us today to speak on the topic vitamin B12 inspired synthetic derivatives for modern applications. Once again, I extend a warm welcome to Professor Dr. J. Shankar. It's over to you, sir.
So now you would try, sir. Now you can try, sir.
Okay. Yeah. Now, it's, can you hear me?
Yes, sir. Yes, sir.
Okay. Yeah. Thank you. Okay. Can you see the screen which I shared? Okay. I assume that it's visible. First of all, good afternoon to all of you, and very happy New Year. And thanks to the organizer for giving us an opportunity to present our research and having arranged some powerful speakers. And earlier two lectures were very interesting, and literally I was happy to be attending this conference. And thanks a lot for the help as well as the efforts taken by the faculty members of the department. And thanks a lot for the students to be here. And today I will be talking about a topic which is somewhat bio-inspired, and this is also going to be in the same line of Professor Kannan, what he was talking about the previous lecture. So this is not on the metallic part, but actually I will be working from the molecular part of it, not the material point of it. Okay. And our work spans, as mentioned by the introduction, that we work on inorganic chemistry. Basically, I am an inorganic chemist, but we work on organic materials and the molecules inspired by the bioinorganic chemistry. So in this talk, especially, I have chosen to take a synthetic derivative which is related to vitamin B12, and can we use these materials which are basically from biology origin, and can we use it for physics applications? Okay, so this is the kind of aim which I am going to talk about it. It is just opposite to that of what Kannan was talking in the previous one. There they are taking something which is inspired by materials and physics, and then they are using it for biology, and in our case we are doing the other way around. Okay, and these are the objectives that we are trying to address in our research. So we want to make molecules which are absorbing in near infrared. So this near infrared range is very much useful in biology as well as in medicine. So that is the main reason behind this, that we are going for molecules which are absorbing in near infrared. Why this is so important is that, why this topic is so important is, if you have any molecule, these molecules have some absorption in the visible region. Okay, and some of the molecules can have absorption in longer wavelength region. If you keep redshifting this absorption towards a longer region, at one point you will be reaching a region which is called near infrared that we will not be able to see. This starts from 750 nanometers till it goes up to 1500 to 2000 nanometer. And this is the range we are talking about, near infrared. So we have to make molecules which absorb in this region. Those molecules can be useful for light harvesting, for organics, photovoltaic cells, that I will be discussing about it a little later. And these molecules can be used for bioimaging also, because they are going to absorb in near infrared. So it's not going to be a problematic wavelength which is going to be helpful for biology. And there is another research which is nothing but treating cancer using light. So this method is called photodynamic therapy. For that particular therapy, you need molecules which are going to be excited by light, and after excited by light, then these molecules become active, and then they actually sensitize oxygen in the body, and the oxygen becomes singlet oxygen, and then that becomes a cytotoxic agent. So for that, the light what we are using is, we cannot use UV light because it's going to be biological tissue. So you need to use a wavelength which is not going to be detrimental for the biology. So that is why near infrared is again becoming important here. And you might have heard about night vision cameras. For example, you cannot use the same camera what we are having in our mobile to take a photo in the night, mid of the night, without any light. Okay, so in that case, your camera detector should be having ability to see photons which are coming from near infrared wavelengths. So for that also, this class of molecules are going to be important. Okay, so this is why we are working in class of molecules which they absorb or emit in near infrared. Number two, the other area is basically in an inorganic chemistry perspective, wherein we want to make molecular assemblies in which you have more than one metals, and means it's not the same metal, but it can be different metal ions which are going to be in a single molecule itself, and they'll be in different oxidation states. This is synthetically very challenging because we wanted to mimic some enzyme models in which you will be having more than one metal ion, say for example iron and copper, and iron will be in +2 oxidation state and copper will be +2 oxidation state, and iron can go to +3 and the copper still remains as +2. So these kind of things, can we do it in synthetic models? That's what we are trying in this case. Again, this class of molecules can also be used for near infrared light harvesting. And when you have more than one metal ion in a particular molecule, these metal ions can talk to each other, and then both of them can catalyze a reaction in a cooperative way. Because of the presence of one metal, the other metal becomes more effective, and vice versa. And another interesting application is these molecules, when you are going to have transition metal ions which are going to have variable oxidation states, and they will be invariably having magnetic properties, so they can be used as magnetic materials also. One fundamental interest in these cases is that there may be an option that you can stabilize an oxidation state which is unusual for a particular metal ion. Say for example, in the case of copper, you may have seen copper 1 and copper 2. because copper iodide is used very well in all the organic cross-coupling reactions. And copper 2 plus, anyway, you might be knowing copper acetate is an example. But how many such examples you have seen in copper 3? So those kind of molecules can be stabilized using, so those kind of metal ions can be stabilized using molecules what we are talking about. So these are the main objectives that we are working on. Today I will not be talking about all these topics. I will be talking mainly about this oxidation state, and then I will try to make it as simple as possible so that even an undergraduate student will be able to understand. Okay, that's my aim today. So these are the molecular tools which we are using. And the first tool, whatever I have here, is Rylan diamides. And sorry, pointer. So this is one basic organic molecule, and this molecule has a high fluorescence quantum, and therefore these molecules are highly useful in organic electronics, like for example display technologies and so on. And these molecules are electron deficient, so they can be used as N-type semiconductors. And these molecules are fluorescent, so they can be used as bioimaging molecules. Photovoltaics, we can use them, and photoredox catalysis, these molecules are already known. Okay, these are some of the publications which we have published in this particular area. And the second one is corrols. Basically, today's talk is going to be completely on this particular molecule, so I will not explain anything here. We will go to the next slide that we will discuss. And we also work on something called Bodipine. This is one of the highly, fluorescent molecule, which is used by most of the biological research community. Okay, so we want to synthesize on different Bodipine molecules which can absorb in different wavelengths, and we can use it for further applications. So, and the combinations between these molecules that we work on, and for depending on what is our requirement and what applications we are aiming at. Okay. Now let's go to the main topic of today's talk. You might have seen that this particular molecule, you might remember that hemoglobin that Professor Natarajan was talking about. In hemoglobin, the name heme is coming because of a group like this. Okay, so this is a tetrapyrrole, and which is each pyrrole unit is connected by one carbon. This carbon is called methyne carbons, and this is also called meso positions. These positions are called meso positions, and these positions are called beta positions, and this position is alpha position. Okay, so just for you don't need to remember this, but I will tell you what this is the important. What is important here to understand. If you see the structure here, you have 4 pyrroles which are connected by 4 carbons. And if I remove one of these carbons, okay, and what you are having is corrol. So in this case also you have 4 pyrroles, but only 3 carbons are connecting all the 4 pyrroles, and 1 pyrrole is connected to another pyrrole directly. This is called corrol and this is called porphyrin. Both of them have this double bonds, right? If you count this number of double bonds, you might be having 11 double bonds. So if you have 11 double bonds, the number of electrons which are involved are 22. But if you see the thick line which I have given here, this line is the one which shows that what is the concept. So if you have benzene, you have 3 double bonds. So they are going to give you 6 pi electrons. The same way, in this place, you have 9 double bonds are going to be in conjugation, and this 9 double bonds are going to give me that 18 electrons. If you remember the Huckel's aromatic rule, if you have 4n plus 2 electrons, then this molecule is supposed to be aromatic. Okay, 18 is 4n plus 2, n is going to be 4, so this molecule is aromatic. Even after the loss of 1 carbon, this corrol also becomes aromatic because this is also having 18 pi electrons. So basically, these 2 molecules should be behaving more or less the same without having any huge difference in properties. Okay, that's what we aim. Now, why this molecule is so important, why the corrol becomes more important is this porphyrin has been well studied, well established for last 60-70 years. People are working on it. But this molecule is comparatively less explored. Now, the question comes, why this molecule has to be explored? Already porphyrin is done. So what new things you are going to give in corrol? You see the structure of this molecule, the basic framework, and this is vitamin B12's basic framework. Okay, so this ring is the one which is called corrin ring in the case of vitamin B12. But This molecule is not aromatic. If you see that there is no conjugation, even though you have some double bonds there, but they are not in conjugation. So this molecule is not aromatic. And this molecule, Carol, was a side product when people wanted to synthesize this particular derivative. Okay. So from there, the chemistry started in 1965. This is the first report where they published the synthesis of Carol. And after some time, this molecule was somehow buried in a lot of literature, which was mostly on porphyrins. So no one showed much interest on Carols. Therefore, its importance was not felt. And slowly now people are trying to understand. In the recent last decade, huge amount of research came on Carols than porphyrins. So that is the main aim of today's talk, that I want to highlight what is the application of Carol, what is the special property of Carol, and how we can utilize them. Okay. Now some of them are here. This inside core, if you see that, you have 3 NH here, but in the case of porphyrin, you have only 2 NH. What is the first implication? The first implication is, if I want to have a metal ion here, this ligand has to deprotonate these 2 positions so that N minus will be there on both the places. Advantage it's going to give me. Now you see that any time you are using a metal ion as a catalyst, you always look for metal ions in a higher oxidation state. Okay, so when you have metal ions in a higher oxidation state, they will be having more catalytic importance than the metal ion which is there in lower oxidation state. That's the advantage that this ligand is offering me. That is number 1. And these 3 inner NH hydrogens are highly acidic, so you can easily deprotonate them. So, and because of that, they become more reactive, stabilizing metals in higher oxidation state, as I mentioned to you. They have a large absorption coefficient. So absorption coefficient, you might be remembering that's Lambert-Pierce law. The molar extension coefficient is the one which I am talking about here, epsilon. Okay, and these molecules absorb really intense. They used to be in purple color, and if you have 10 to the power minus 5 molar solution, still the compound you can see the color will be visible. So it is so intensely colored. And this molecule, which has less carbon, but it has the same number of pi electrons. Therefore, this is a little bit electron rich compared to that of porphyrin. Okay, so if it is electron rich, that means that it can be easily oxidized. So I will explain why this oxidation becomes more important. So where and all this has been applied. So these molecules have found application in redox catalysts, light harvesting in solar cell because of the large absorption coefficient, bioimaging because of the emission, and for cancer therapy, as I mentioned earlier, in photodynamic therapy, and as chemosensors, because you have 3 NH here, and if I remove this 3H, then I will be having N minus 3 times, so I can bind any metal ion which is going to be in +3 oxidation state, and thereby I can use this molecule as a sensor. Okay, instead of catalyst, I can use it as a sensor. So this is where these are the applications. But when you say that one molecule is there, and if it is really useful, why people were not using for this many days? Okay, so there were some problems. So now we have to look into what are the problems which were there. So this is basically the absorption spectra of these molecules. Both porphyrin and Carol, they will be having a very intense absorption around 400 nanometer region. This is called a solid band, and smaller intense bands which are there on the red side or the long wavelength region around 600. They are called Q bands. Okay. And most of the porphyrins are named, or the enzymes which are given numbers, for example, cytochrome P450. That 450 is nothing but absorption maximum of the particular enzyme. Okay, so the solid band is so important to name a particular porphyrin, because it is fingerprint is, for every porphyrin there is a fingerprint, and that fingerprint is nothing but the solid band and the Q bands. And these are the HOMO and LUMO of how these molecules look like. So this is the HOMO, which is having the electron density which is delocalized, and the LUMO is the one which is going to look like this one. Okay, and there is a Goderman 4-orbital model, and this is basically on the symmetry of this molecule, and the basis of it they predict that this molecule is supposed to give this class of absorption spectra. Okay, we don't need to go much into the detail of this one. I just wanted to give you the information. And this much information is quite good enough for the topic what we are going to discuss now. Now, what is the issue with metal corals? That's what I wanted to tell you. As I mentioned, corals can stabilize metal ions in +3 oxidation state. Okay. And I told you the example also. You might have seen copper 2 plus very often, but I don't think you will be able to count at least 2 complexes wherein you have seen copper in +3 oxidation state. You may not be able to do. Okay, so it's so difficult. But the coral ligand, what it has done is it binds copper and forms a neutral complex. Okay, and if it is forming a neutral complex, as I mentioned earlier, coral is a trianionic ligand. Trianionic ligand means it is giving me N minus, N minus, N minus. So then the metal ion which is going to sit inside and then forms a neutral complex, then the metal ion is in +3 oxidation state. Okay. But people are not willing to listen. They are not going to believe that you are having copper 3 here. Okay, because stabilizing copper 3 is difficult. But this molecule shows that the copper 3 is stabilized. So now I have to prove that this molecule actually has copper 3. It is not copper 2. How to do it? We'll come to the problem again. The same problem with respect to Fe3 or Fe4. What is there inside here? If this chlorine is not there, the iron is supposed to be +3, and the chlorine is also there. So one more anion is added, so it has become iron 4. Is it true? This is iron 4 or it is iron 3? Okay, this is question. So this question is there everywhere with all the molecules, all the metal ions, whatever which is binding to coral. Why is so important? Why should we first of all worry about the oxidation state, sir? If I don't know the oxidation state, still I can use the molecule. If you want to use these molecules for catalysis, you need to know the precise oxidation state of these molecules. Otherwise, you will not be able to understand what is happening in the catalysis step. Or if you want to improve the catalyst or catalytic action of the particular complex, you need to know all the electronic information on the catalyst. For that, the oxidation state becomes really important. Okay, that's where this assigning the oxidation state becomes crucial, and that opens up discussion or the debates about which is the oxidation state which is correct. There is no ambiguity how to assign the oxidation states. Now let's go to the origin of this problem. As I mentioned, coral was reported in 1965. So 65 is quite far away, okay? And now this is the reaction scheme reported by the authors in 1965. You take this ligand, you added some copper salt, and then you are getting copper complex here. What you have here is the copper is in +2 oxidation state as assigned by the authors. What they have mentioned is, they also thought about this, that if this metal ion is binding here, then it has to be copper 3+, but copper is not in 3+, but it is supposed to be only 2+. So they have not removed one NH, they have removed only 2 NH. And then copper 2 is sitting here comfortably. And this is what is reported. There is no other further information on this because it was 1965. They may not have had access to further instrumentation technique. Now I just wanted to bring to your notice, copper 2 is a D9 system. So you have one unpaired electron. If you have one unpaired electron, this molecule is supposed to give me an EPR spectrum. Okay. By that, I can say that this is copper 2 or copper 3. If it is copper 3, then it is going to be D8 system. D8 system in square planar becomes diamagnetic, so it will not give me EPR. But D9 system in square planar is supposed to have one unpaired electron, so it is going to give me EPR. So simple, sir, that I could have already found it. People have done that as well. 1997. So now you are coming after 30 years. Again, another group is working on it. This is Emanuel Vogel from Germany. They have added this copper, adding copper salt. They assigned this copper as copper 3. They have not shown the hydrogen here. Okay. Now, how will you prove that it's copper 3? The molecule, I told you, if it is copper 3, it's a D8 system. If it is a D8 system, then what you are going to have is a square planar complex is diamagnetic. If it is diamagnetic, that molecule is supposed to give me an NMR spectrum. They are getting the NMR spectrum. So now you see this. This is 386. It's a higher temperatures. Okay, so 293 is supposed to be our room temperature, and in this case, you are going for -17. So in -70, you are seeing a very sharp spectrum, and when you go to higher temperature, you are getting a little broader. Okay, this is what they observed, but not much information could be derived out of it. What they proposed is that this copper, what is there inside this curve, is not purely copper 3+, but rather it is going to be in copper 2 with a radical again outside. So this point needs a little bit of elaboration. I just wanted to tell you. This ligand, forget about this copper 2 now, this ligand can act as a dianionic radical. So what dianionic radical means? Now the previous slide, if you go, this is a dianion because two NHs are removed. This NH and this NH are removed, so dianion. And this nitrogen is bound to this hydrogen. Now you break this bond. When you break this bond, what you are going to have is one electron is going to go with hydrogen, another electron is going to stay with nitrogen. And as soon as this electron is staying here, that electron is going to be delocalized as a radical, and therefore you are having a radical here. Okay, so this is one possibility. So one electron has been given to copper. So the copper +3 has become +2, and as the ligand has given one electron to the copper, so it is going to have one unpaired electron. So that is going to be a radical. So now, if you look at from that point, you have one unpaired electron on copper because now it is copper 2, and another unpaired electron on the ligand. So two unpaired electrons are going to be in the same molecule. They can be in two orientations. One is going to be both the unpaired electrons are aligned. Okay, this is called triplet state. And another state is that these unpaired electrons can go anti-parallel. When they go anti-parallel, then what you're having is a singlet state. So when you go for a triplet state, then the molecule is going to be still paramagnetic. But when you go for singlet state, then what you are having is one upspin, one downspin. So they are paired. So you are having a diamagnetic state. Okay. In this case, when you go to lower temperature, what they say is that this particular molecule goes to singlet state. This is called antiferromagnetic coupling. Because of this antiferromagnetic coupling, the molecule becomes diamagnetic. That is why NMR becomes very short. But when you increase the temperature, what happens is the electrons which were paired at low temperature actually becomes parallel to each other. And when they become parallel to each other, then they become paramagnetic. Once they become paramagnetic, then my NMR gets broader. Okay. So this is a proposal. No one has seen that copper is in +2 oxidation state, but this is the only way by which you can prove that this is happening. And another evidence what they gave is that in the crystal structures, the solid state structure of this compound, by X-ray diffraction, when they saw that both two molecules come close to each other and then they stack over each other. So when they are stacking, there can be another antiferromagnetic coupling between the copper and copper, and as a result of this, they become diamagnetic. That's why your NMR is becoming shorter. This is the argument. And after that, this work was taken over by Glory in 2007, and they have given another different explanation. Meanwhile, 2015, from India, another report comes which says that already the discussion is going on whether it's copper 2 or copper 3. And now another work comes and then it says that I can stabilize copper in +4. See here. So +4 oxidation state. Okay, so this is a existence of copper 2, copper 3, and copper 4 in copper carbohydrate complexes. Okay. So this opened up discussions in a much vigorous way, and then people started looking into this. Meanwhile, there was parallelly another research was going on by Daniel Nocera from US. So these guys were working on the same direction, and there is another group which was electrochemical group. They were also working on the same class of molecules. What they said is, you have this role which is having 3 NH. Now you add this copper 2+. Once you add copper 2+, the first copper 2+ ion, it takes 1 electron, okay, and then it becomes, this ligand becomes radical, and it still has 2 NH here, okay. Another copper 2+ comes inside, and that guy goes and sits inside, and then you are having now copper 2+, and the radical is also going to have 1 electron, and these are the two different orientations. This is antiferromagnetic because both are in opposite direction, and this is ferromagnetic. It is going to be in the same direction. Okay, so these are the proposals. What Nocera did is, these are the molecular orbital diagrams of the copper 2 complex. This is the metal orbital and these are the ligand orbitals. If I take this argument as the correct argument, then the electron, one electron, whatever you have in the copper is supposed to be in d x square minus y square, because x square minus y square is the highest energy orbital in this case because it's a square planar. Okay, and one electron is there, and another electron on the radical on the ligand, which is also going to be a free electron. Now, if I oxidize this, oxidation in the sense that I am going to remove one electron from this molecule. If the electron is removed from the ligand, this is the one which is going to be removed, then what you are having is you have an active copper 2 plus, which is not having another unpaired electron to interact. As a result of this, this ligand, this particular copper 2 plus is supposed to give me an EPR signal. They oxidized, they removed this one electron from here, and then they got a cation, and the copper 2 plus is residing there because only the ligand is getting oxidized, not the metal. Okay, and they are getting EPR signal. Okay, and the copper I value is 3/2. As a result of this, you will be seeing 4 set of peaks. It's called hyperfine splitting. And the finer lines, whatever you are seeing, are because of super hyperfine splitting. That is happening because of the 4 nitrogens what you have here. Okay. Okay, sir. Now, if I reduce, where the electron is going to go, whether it is going to the copper or it is going to the ligand. Add one more electron. Now, the electron again goes to the ligand. So now, this unpaired electron again doesn't have any more unpaired electron to interact with each other. So this is going to behave like a simple copper 2 plus, and this also gives an EPR spectrum. So what it proves is that this study proved that the copper which is there in corol is staying as a copper 2 plus. It's not copper 3 plus, but because of the unpaired electron which is there in the ligand, these guys behave like diamagnetic, but it is not purely diamagnetic. It is because of antiferromagnetic coupling, they become diamagnetic. So till now, whatever the discussions which has been done, everything is basically when you have a metal inside, then only you can say this. Without that, no one has seen this. The free ligand without any metal ion, which is supposed to be having one radical with the 2 NH inside. So that is not seen. So this is where one report came in 2000 from Ziegros. So this group is from Israel, Technion. They have proved that you take a metal ion, which is gallium. So it is a main group metal ion. Gallium is in the aluminum group, so it is +3 oxidation state, and the +3 oxidation state, and it cannot be oxidized. Okay, it's a redox neutral at this point. So now if I add one electron oxidant, this is called magic glue. This ligand, this chemical's name is magic glue. It's nothing but antimony salt, and what it does is it's a one electron oxidant. It removes one electron from the molecule. So when you have a molecule like this and then you remove one electron, what you are going to have is you are creating a cation radical. So that is a cation radical which has been formed here. Now the question is, it is the metal which got oxidized or the ligand which got oxidized? As I told earlier, gallium is not the metal ion which is going to get oxidized, so it has to be the ligand. So now the ligand has got oxidized, and people have found an EPR signal which is coming for a free electron, which is because of the radical. Now what we wanted to see is that, is it true that you are having a structure which is having 2 NH and then 1 radical, or it is something different in this case? So the two possibilities what can happen is, you take gallium now instead of copper, oxidize it, so you are getting this same cation radical, and you oxidize it adding an anion. What is supposed to happen is, if the metal is going to get oxidized, okay, then you are going to have an anion bound on the metal. Okay, so that is going to say that whether this ligand is innocent or non-innocent. So this is a new word which is coming here. Why we call this as an innocent and non-innocent is that if a metal ion which is going to participate in redox, okay, then that metal ion is only going to participate in redox process. Say for example, in this case, if I oxidize this particular complex, if the metal is getting oxidized and the ligand is just keeping quiet, then this ligand is innocent. It is not participating in a redox process. But when I oxidize this compound, if the ligand gets oxidized instead of the metal, then what I say is that the ligand is participating in the redox process. So we say that this ligand is supposed to be non-innocence. So this is what we wanted to see, whether we have innocence or non-innocence with that of corol with other complexes. This is already proved that Carol can act as a non-innocent ligand by electrochemical studies, but no one has seen the structure. So they don't know which species they are talking about, but in this case, they proved that electrochemically this is possible. So this is the person I mentioned to you a little early, Martin Roering. What they did is they wanted to metallate this Carol with tungsten. When they tried this metallation at 200 degrees Celsius for 8 hours in benzoyl as a solvent, they got a product in 4 to 7% yield. Okay, this is the product. They didn't know. They send the species for NMR. This is the routine procedure for synthetic chemists. Once you make the compound, then you send it for NMR in mass. When they sent for NMR, there was no signal in NMR. So only one possibility is either you have not got the compound, or you have got the compound which is not going to be NMR active. The first question is solved because these are the compounds which are highly colored. So you know that the solution which you gave for NMR is colored, so you have the compound inside. That means this compound is not giving NMR, so why don't you try EPR? They recorded EPR and then they saw a signal. And that is how it was allotted that or assigned that this compound is a paramagnetic compound and it may be a radical. Fortunately, they could get a single crystal X-ray diffraction structure. That means you take a compound, you crystallize this and keep it in X-ray crystallographic diffraction measurement, and then you will be getting diffraction patterns. And when you solve the data which is coming from diffraction patterns, you will be able to see the structure. Okay, so this is one of the very common technique which is used by most of the inorganic chemists. So they use the same technique to find out the structure of this molecule. Now you see the beauty of this molecule. This is not having 3 NH inside, they have only 2 NH. Okay, and the molecule did not give NMR, so you have a radical. So now what you have is you have a dianionic radical. So this is the first proof which stated that yes, this is the species which is forming and which is giving me the NMR in the case of copper case. Okay, this was the final proof which gave us. But in our case, we wanted to see that this is going to happen in the case of gallium or not. We took the gallium complex, added the same magic blue which was added by the Zebras group. We saw the EPR spectra. But the problem did not end here. In their case, they just show the NMR and then they were happy. Sorry, EPR and then they were happy. But in our case, when we went for high resolution mass spectra to prove that this species is formed, we could see a lot of chlorinated products. Because if you remember, this magic blue is nothing but SbCl6, which is bound to this tetrabutyl ammonium. So SbCl6 is giving me chlorine, and that's why this chlorinated products are forming. Okay, this was the conclusion by the student. Now the next is, sir, how to stop this chlorination? Otherwise, we will not be able to see anything. Okay, you block the positions wherever chlorination can happen. You block it with something. Then after that, you do the same reaction. These are the 2 active positions on the Carol, and you block both the positions. Now you add magic blue. Again, you are getting chlorination. Okay, so then what is happening here? Your EPR is coming because the radical is forming, but chlorination is also happening. Block all the beta positions. Okay, so these are the beta positions. Block all of them with bromine. There is no place for chlorination. Add magic blue. Again, you are getting chlorination. Okay, and EPR is also coming. So that proved that the molecule what we have got is nothing but gallium, which is having a chlorine on the gallium. But the ligand what we have here is 2 NH and 1 radical. This is the crystal structure what was got by Martin Roering. The same thing which we are having with gallium. So how you are so confident that gallium is +3? Yes, you have a radical here and you have 2 NH. This molecule gives EPR, and we could get a crystal structure of this molecule as well. So I am showing this structure from the top angle. So it is showing you 4 pyrols, and these are the pentafluorophenyl rings which are here, and the 2 carbonyl groups. And when you see from the side, then you are seeing the gallium here, and it is bound to this chlorine. So the chlorine is there because this ligand is giving me only dianionic charge now, but the gallium is supposed to be +3 oxidation state. So it needs 1 anion. That anion is coming from the SbCl6, whatever we added there, and it has taken the chlorine from there, and then it has become gallium 3. So now this is a neutral complex. This is the first time that you could get a metallated radical. For that we could get a crystal structure for that. And then we proved that you don't need to have a d orbital to stabilize this kind of radicals, because the earlier case I did not tell you there. When you go here, we have mentioned that this particular work which was done by Nozera, they mentioned that the HOMO of the curve and the dz square or dx square minus y square of the transition metal have to have a proper orientation energy wise, otherwise this is not going to be stabilized. Okay. But in our case, when we went, we have not having any metal ion which is going to have a d orbital. In this case, the gallium case, we don't have any d orbital which is available for bonding by any of this ligand orbitals. Still, this particular species can be stabilized, and this is what we wanted to prove in this case. Okay, so this is our one of this earlier results in this direction, and we could prove that curve can act as innocent as well as non-innocent, depending on what kind of substitutions you are having, what metal ion you are going to have in this molecules. Okay. Now we have tried various calculations, spin density using density field theory we have calculated, and we could see that the radical is highly delocalized. This is showing that the radicals are going to be highly delocalized. And there are other calculations which says that whether it's a delocalized or not. This is called harmonic oscillator model of aromaticity. This index is called a HOMO index. So this HOMO index is supposed to be 1 for benzene. What it means is, in benzene, if you say that it is aromatic, you have all the bond lengths the same. Okay, all the CC bond lengths are supposed to be same. If it is same, then it is going to be, HOMO is going to be 1. But if you have bond length alternation, single bond, double bond, then what we have is the delocalization is not complete. So that means that the delocalization is not efficient. So this molecule is supposed to be less aromatic. So you have to calculate this one. And when we calculate originally for benzene, the value is to come around 0.7. It's not 1 even for benzene. So in this cases, we calculated the same values for these molecules from the bond lengths, whatever we calculated from the single crystal XRD diffraction data. And it is coming as 0.7. So that means this molecule is equally aromatic like that of benzene. When you go for gallium complex, again it is aromatic. And when you go for gallium with 2 pyridyl in the axial position, then also this is aromatic. Fine. Now, the question comes here. Huckel's aromaticity rule says that if you have 4n plus 2 electrons, then it is aromatic. If you have 4n electrons, it becomes anti-aromatic. Okay. Now the question is, if I have 4n plus 1 electron, should I consider as 4n plus 1, or it is going to be considered as 4n minus 1? Okay. In both the cases, it is going to be a problem. Either it has to be aromatic or it has to be anti-aromatic. So there is nothing very clear about this, but in this case, we could calculate this HOMO value for the radicals, whatever we have made here. And in that case, you can see that this value is coming to be very good compared to become supposed to be aromatic. And when you are going to have all the bromines here, the value goes down a little bit. And when you have CHO, the value again goes to 701. More or less it is same. Okay, so the one which is calculated from the density function theory and the crystal structure, whatever we have, both the values are matching. That says that even though it's a radical, it still maintains its aromatic character, and therefore we can assume that the radical, whatever we have here, it still has a delocalization. That's why we are seeing a broad APS spectra, but we are not having any super hyperfine splitting which is coming because of nitrogen. And these are other calculations. It's called nuclear independent chemical shift values. And this also confirms that this molecule is aromatic. This is another calculation which is called anisotropy induced current density. If this direction of these arrows, if you see that the small arrows, whatever we have here, if these arrows are going to be in clockwise direction, that is supposed to be aromatic. If it is going to be anti-clockwise, then this is supposed to be anti-aromatic. So till now, whatever I was talking to you earlier, everything was basically I was talking to you